In this video, we shall derive the relation between electric field and electric potential. That is, E is equal to negative gradient of potential. It can also be written as grad V. This relation is very useful to find vector electric field from the scalar electric potential. Let us start our discussion with a very well-known equation, that is electric potential V is given by the line integral of electric field. That is, V is equal to line integral of E over given path. Path can be taken as limit. So this equation is known to us. Using this equation, we have found electric potential from E. But now, I would like to calculate electric field E from electric potential V. So, I would like to bring this E out of this integration. So, have to make E constant. So, I would like to choose a small path. That is path D delta L. Delta L is an incremental path over which electric field remains constant. When the electric field is constant, then solving this integration becomes very easy. When the path is very small, electric potential across the path is also very small. That means delta V is equal to minus E dot delta L. So delta L is the incremental path. Delta V is the incremental potential over the incremental path. So the right side of the equation is a dot product which can be expanded as E cos theta into delta L. Here, theta is the angle between the electric field E and the path delta L. Delta L. So, from this diagram, we can make some conclusions. First one is, when theta is 90 degree, cos 90 becomes 0. So the potential difference goes to 0. That means when the charges are being moved perpendicular to electric field, no work is done. No energy is expended. So potential difference is also 0. When theta is 0 degree, that is, if the unit positive charge is moving in the direction exactly opposite to electric field, then the angle between E and delta L becomes 0. When they are 0, cos theta becomes cos 0, that is equal to 1. So that is the maximum value of cos function. So when theta equal to 0, we will get the maximum change in potential with respect to distance. So we can write the next simple equation as delta V by delta L max is equal to minus E. So cos theta is 1 here. So cos theta is represented by this term, maximum rate of change of potential with respect to the distance. We can proceed to the limiting case also. So at the limit, delta L tends to 0, we get dV by dl max. That is equal to negative electric field. So the minus sign indicates that the charge is moving opposite to electric field. The maximum rate of change of potential is in the direction opposite to electric field. So this equation gives us the magnitude of electric field. So we can take electric field to the left side, then it is equal to minus dV by dl max. So that means the magnitude of, from this a very important conclusion can be drawn, that magnitude of electric field is equal to maximum rate of change of potential. So very useful information. The electric field is always calculated from the maximum rate of change of potential with respect to distance. Now we shall find where this maximum change is occurring. So for that, let us go with some example. Let us consider a point charge Q. The potential for this point charge is given by V equal to Q by 4 pi epsilon R. So Q is the point charge, that is constant value, 4 pi epsilon is also constant R. So the potential is inversely proportional to R. If you choose a spherical surface taking the charge at the center origin, then the radius can be R here. The potential is given by the V. And if you find the potential due to the same charge at another point on the sphere, there also potential is same. That means the potential remains constant on the entire surface of the sphere. So we can declare the spherical surface as equipotential surface. Equipotential surface. That means all the points on the spherical surface will have the same potential value. Also, we can say that the potential difference between any 2 points on the sphere will be equal to 0. So equipotential surface is the one for which potential difference between any 2 points will always be 0. So this is a very useful surface which will give more idea or more information to us. Now let us consider electric field of this point charge. Electric field of this point charge is given by E equal to Q by 4 pi epsilon R square. E is a vector. So the direction is A cap R for a point charge. A cap R is the unit vector pointing outward from the charge perpendicular to the spherical surface. So the direction of electric field E is always perpendicular to the spherical surface. So A cap R is the direction of the electric field. Now, if we consider the potential is also changing with respect to R. As the R increases, potential decreases. As the R decreases, potential increases. So maximum change in the potential happens along the radius of the sphere. If R is kept constant, potential does not change. So potential changes with respect to R in the direction of A cap R, or in the direction of electric field. So the maximum potential change dV by dl max happens in the direction of electric field only. That is opposite to the electric field, and that is perpendicular to the spherical surface. So maximum change in potential, the rate of change of potential, that means direction of electric field is perpendicular to equipotential surface. Also, the maximum rate of change of electric field also occurs perpendicular to electric field, perpendicular to equipotential surface. Right. So keeping this in mind, I can introduce the direction of electric field into my equation. That is E, which was written as dV by dl max, now can be converted to vector form just by writing A cap R, which I don't want to write R here. I would like to write A cap L. So A cap L is the unit vector pointing along dl. So the dl vector, distance vector, which can be expanded as dl into A cap L. So A cap L is the direction of the path over which the charge is moving, or it is the path over which the maximum potential is occurring. So in the point charge case, A cap L is A cap R, the radial one. So this changes according to the charge distribution. So now I would like to generalize this equation in a better way. Since maximum change of potential happens perpendicular to equipotential surfaces only, so my next equation would be E is equal to minus dV by dN A cap N. This makes some useful condition. Here, we consider equipotential surfaces. These are the surfaces over which potential remains constant. For example, on the outermost surface, potential may be V1 throughout the surface, second one V2, and the third one V3, maybe like this. So each surface is having a constant value of potential. If these are equipotential surfaces, then the electric field direction, as per our discussion, would always be perpendicular to equipotential surface. And also the maximum rate of change of electric potential happens perpendicular to equipotential surface and opposite to electric field. So this is going to be the direction called A cap n. So A cap n is the unit vector perpendicular to equipotential surfaces as well as opposite to the direction of the electric field. That is, this is going to be the direction of the electric field. So both are perpendicular to equipotential surfaces. dn corresponds to the normal distance or the distance perpendicular to equipotential surface. So A cap n is the direction of dn. So let us call this equation 1, and we shall leave it here. Next, I would like to use one of the equations from mathematics, that is definition of gradient. Of a scalar. So from the literature, we can have the definition of the gradient, which is defined by gradient of any scalar t is simply rate of change of t with respect to normal distance, and this gradient is a vector operation, but it is performed over a scalar, and it is having a unit vector A cap n, which is the direction of dn or delta n. Equation number 2. So from equation 1 and 2, we can write that E is equal to negative gradient of potential. So in mathematics says that any scalar quantity, that is t, can produce gradient provided it has some partial derivatives. So in our case, in place of t, we have electric potential. So the electric field is given by negative gradient of electric potential. This proves some part of our question. In the next part of this discussion, we shall write the mathematical expression for finding gradient of potential V. We know that electric potential, a scalar quantity, V is a unique function of x, y, z in Cartesian coordinate system. That means V being a scalar quantity, it is a function of all the three variables x, y, and z, and V can be expressed in any of the coordinate system depending upon our convenience. We find always Cartesian is quite comfortable, so we would like to write a relation for V in terms of partial derivatives. That is, change in V can be expressed as rate of change of V in terms of all the variables x, y, and z. So in this equation, we can observe that the potential is changing with respect to all x, y, and z, and the rate of change of potential V with respect to x and with y and with z are different. So potential can vary in different rates with the different variables. So based on that, the total change in potential will be calculated as the sum of the changing potentials in different directions in x, y, and z directions. So in this case, potential is a scalar quantity. So the right side equation is also scalar. So you are not going to find any unit vectors on the right hand side equation. You have to be careful in that. So let us designate this equation as equation 4. On the right side, if we make an attempt, we can introduce unit vectors by mathematical interpretation. That is, we know that dV is equal to minus E dot dl. This equation comes from delta V equal to minus E dot delta L. This equation we have used already in the beginning of the discussion itself, and which was taken from V is equal to minus E dot dl. We know this one. So we have two equations available here for dV. One is in terms of vectors, another one partial derivatives. So with little bit effort, we can combine these two to get very useful equation. Let us go in this way. We shall expand this flow. Here, E is a vector, so it can be expressed in terms of its components. That is x, y, and z components in Cartesian coordinates. Similarly, the differential length dl can also be expressed as its components. So in this equation, we have differential quantities. Now, if we perform dot product, we'll end up with the equation Ex into dx. We know that in dot product, the corresponding components will be multiplied. Ey, dy, ez, dz. So ax dot ax is 1, ax dot ay is 0, ax dot az is 0. So corresponding components should be multiplied. All other components will be 0. So we have this relation. And we can designate this as a continuation of previous relation. Equation number 5. Now let us compare equation 4 and equation 5. That is this one and this one. Left side both are dV. So right side must be equal. By comparing left side and right side, we can get the relation ES equal to. So EX equal to minus dou V by dou X. We can get this equation just by observation. Similarly, the Y component of electric field would be dou v by dou y, and the z component minus dou v by dou z. See, we have all the three components of the field here. So we can combine them to get the vector electric field, that is Ex a cap x Ey a cap y plus Ez a cap z. So E is in Cartesian coordinate system. Now just by substituting for the components, we can have minus dou v by dou x a cap x minus dou v by dou y a cap y minus dou v by dou z a cap z. So electric field is expressed as partial derivatives in vector form. And in the next step, I can take out minus, and also I can take out v. V is a scalar function, so it can be taken out. So what we are left with is dou by dou x, dou by dou y, and dou by dou z. So this term does not include any physical quantity there. That is, any physical quantity like electric field, electric potential, electric flux. It's just a mathematical operation. So this becomes a mathematical operator which is denoted by del, and potential remains V. So this complete vector is denoted as del. So we got here the expected result minus del V. So if we combine all the equations what we derived in the very beginning stage, we wrote electric field as gradient of potential, and now we have expressed it as minus del V. So this can be treated as the relation between electric potential and electric field. And this equation only gives the dimension of volts per meter to the electric field. If you look at this equation here, electric field is given by dou v by dou x. Dou v, change in potential, volts, change in distance, x, that is meter. So from this equation, we can say that electric field is having a dimension of volts per meter. So the unit of electric field is volts per meter, and this is the very useful relation between E and V. Lastly, we can say that electric field is given by the differentiation of electric potential. In the very beginning, I told that electric potential is given by integration of electric field. That is, electric potential is given by integration of electric field. So potential is the integral of field. And here in the last equation, can say that electric field is given by the differentiation of electric potential. In this case, what I have done, dou by dou y, dou v by dou y, and dou v by dou z, I have assumed 0 time for time being. So dv by dx. Potential is a function of only one variable x. So the partial differentiation becomes definite differentiation. So when the potential changes with more than one variable, we go to partial differentiation. So just for the sake of consideration, I have taken one variable x. So it is dv by dx. So field is the differentiation of the potential. Potential is the integration of the field. That's volts per meter. So that is the result expected from this discussion.